Hello there. Welcome to another problem session. So today we have going to introduce Gauss's law, and we'll continue in future videos. So this Gauss's law for it says the electric field in a static situation. So we're talking about a static electric field. So number one, source charges are fixed. So we're in a frame in which charge is fixed. So for instance, there may be these charges in here, and then if you each one is producing its electric field and goes all over the place, right? Each one is producing its electric field. So if I take a arbitrary surface, so this is say Q1, this is say Q2, this is Q3, let's see just 4 of them. So if I take a surface like this, the Q1 and Q2 are outside, and this is a 3-dimensional surface. So this is 3-dimensional surface, and let's divide this into small patches, and on each patch we do something following. We say, what's the net electric field? Maybe from all of this, outside, inside, whatever, all these charges, maybe electric field is this way here on this patch, and this is in some direction electric field on this patch. So let's call it at patch P, okay? The normal to this patch is in that direction. So this is 90 degrees. Because patch is, we have to take a tangent on the surface to get the normal, right? And so this angle is theta between these two directions. And the area of the patch is P. So if you do this, electric field dot n hat for the patch, because this if I look at this patch, n hat will be in that direction, so it depends on patch, and then the area of the patch. The areas will be all different if I've done uniformly. And if you sum over all patches, okay, so we do this thing. Now this is a mathematical thing we do. Now this is a dot product, and this is a unit vector, unit normal vector. So when you add these up, this is called flux through this surface S. Flux through GH surface S. And it turns out this flux doesn't depend on the outside charges. This is outside S. It only depends on inside charges and doesn't depend on where the charge is inside. So that's actually the very very bold thing. This is equal to sum of charges inside, and doesn't matter where they are, divided by epsilon naught. You may remember K equals to 1 over 4 pi epsilon naught, that constant that went into Coulomb force, right? And this epsilon naught is permittivity of the vacuum. K is 9 times 10 to the power 9, so epsilon naught is 4 pi K, and it's easy to remember for because these 9 are more or less the same, so it's easy to remember K in terms of values. epsilon naught is 8.85 times 10 minus 12 SI units. Okay, if you multiply them, it turns out like that. So this is what is called Gauss's law. That flux will equal to this is Gauss's law, and here it just depends on Q3. You had a Q1 and Q2 was outside, and Q3 and Q4 was inside. So those are only charges. So this will just be Q3 plus Q4. Won't depend on this. Although this is also producing electric field, this is also producing electric field there, but comes to the flux. It will be the electric field from this guy, flux from this guy through this surface will be 0. Okay, so that's if you see if the patches are very small, you can write this as this sum as an integral. It will be an integral which is a closed surface on a closed surface, usually written like that, closed surface S, and it's going to be double integral because it's on a surface, and E dot n hat dA. So you can write like this, or you can do a double like that to remind yourself that this is a surface. And so this is on the right side will be equal to Q enclosed. These are inside, enc for enclosed over epsilon naught. That's the Gauss's law. Now we'll see how Gauss's law can be used in certain very symmetric situations to find electric field, the magnitude of the electric field. This can be used to find the magnitude, formula for the magnitude, because it's solid dot product. So you can see if it's dot product, then I can't get the direction from it, but this formula can be used to find the magnitude of electric field, and we'll learn that. Okay, so let's see over here. From the flux, from Gauss's law, you can see that this does not have anything inside. So this is already flux through S4 is on the right side is going to be 0, since Qn by the S4 is 0. S1 includes both of these charges. So Qn here is going to be plus 5 microcoulomb minus 3 microcoulomb. So it's going to be plus 2 microcoulomb. Qn by S1. So flux through S1, so I don't need to do electric field. I just on the right side, just use that. It's going to be plus 2 microcoulomb over, you have a 8 point SI unit will be this is the opposite of this. So K, a unit of K is Newton meter square over coulomb. So this is going to be a coulomb square. So this is going to be exactly opposite. So this is going to be 8.85 times 10 minus 12 coulomb square over Newton times meter square. And you can microcoulomb, you can just say 10 to the minus 6 coulomb, and you can see that one of the C cancels out, and so this is equal to 2 by 8.85 times 10 raised to the power 5 Newton meter square over coulomb. So you can see electric field times area squared, that's the unit. And then you can just compute this. That's going to be surface S1. So let me erase some of this, get me some space. Okay, so if I look at S2, this surface encloses only this charge. So phi S2 will just be 5 microcoulomb, and so it's going to be 5 microcoulomb over, not the area, it doesn't depend on the area, it's just how much charge is enclosed, and epsilon naught 8.85 times 10 to the power minus 12, and so this 10, make it 10 to the minus 6 same way, coulomb square over Newton meter square. So that's phi S2. How about phi S3? Phi S3 will be minus 3 microcoulomb. So this is going to be, flux will be negative 3 times 10 to the power minus 6 coulomb, 8.85 times 10 minus 12 coulomb square per Newton meter square. Okay, so you just get flux through any surface. If I were to ask you what's the flux through this surface, why, it's going to be, flux will be 0 here, right? If I were to ask you what's the flux through this a bigger surface, S5, flux through S5 will be the same, as there's only 2 charges here. So the same as S1 will be same as flux through S1, and which is that's the answer. Okay, so that's about how you can use to find flux using Gauss's law. You don't have to compute it using electric field. If you knew the electric field and then surface is simple, it is possible to do it directly. But if you don't know the electric field, but you know how the charge is distributed, then you can find the flux. Okay, now we're going to do how do you use Gauss's law? How do you use Gauss's law to find electric field? N hat dA is equal to Q inc over epsilon naught. How do you use to get some find electric field? Okay, and that's certain problems you should know in those problems how to do it. It's really very cute. Okay, so I'm gonna do one by one, get my some more space and clean up. Okay, so I have a charge here. So there's a charge here, and there's a point P. There's a point P over here, and I want to know what's the electric field. We already know the answer to this question, right? If charge Q, we already know the answer. So answer is, if this distance is r and this vector is u hat at point P, so it's a from charge to the point, so the charge to the point P, that direction unit vector, then we know the electric field at P is just equal to kq over r square u hat q to p, right? So that's a already known answer, but we want to use this to find the answer. Okay, so first of all, we'll imagine a surface upon which we know something. So here is a surface. If I take a spherical surface with same distance here, so we know the magnitude of the electric field will be constant here, right? So on this surface, because from its same distance from the charge, number one, since every point, so this is the surface I'm going to imagine, every point at S is same distance from charge q, we we can say magnitude electric field is same at all points of S. So if you look at a patch here, electric field is pointed that way of some magnitude. If you look at a patch over here, electric field is pointed that way, but their magnitude is the same. The vector is the same size. So that's one thing we say. And second thing is each patch, if you look at the normal and the electric field are parallel. So if I do this patch, the normal is radially out, right? This is a ball. Right, so from this is radially out and the electric field. So on each patch, electric field is parallel to n hat. Electric field of the patch is parallel to n. That would mean this dot product, this is of the patch, for the patch, right? Remember? So this is summation on the patch. So is electric field proportional to n hat. So instead of using that way, we say electric field is parallel to n hat, and we can say E dot n hat equals to just E. So this is vector and this is a scalar. It can if this charge is negative, if this charge is if negative, then the electric field will be anti-parallel. So electric field will be that way. So, but it will be this would be plus or minus. Okay, and we would just not distinguish it. We just call it E, and E can be positive or negative. Can be positive or negative. Doesn't put sign over there. We just absorb the sign in the E. So unlike the vector magnitude, this is going to be a positive or negative. Okay. So if I look at this formula here, in this formula, over this surface we have E dA, and E is constant at each point. So this thing can come outside the integral. Okay, so this just becomes, so this is left side of this equation. It just becomes E surface dA. So this is, so the full area of the surface is E times 4 pi, and the radius is little r is square. So right side is how much charge is enclosed. It just Q is enclosed. That's all I need to know. It's just Q over epsilon naught. So from these two I can write E equals E times 4 pi r square equals Q over epsilon naught. And so the magnitude E is Q over 4 pi epsilon naught r square, and this K is 1 over 4 pi epsilon naught. So you can see that this this gives the vector formula, but this gives us a magnitude. And knowing that electric field is always in for a point charge is radially outward, we can write down this thing as a vector. So I'm not done yet. To get the electric field, we will write electric field is this stuff, E times U hat from the charge to the point P. So this is some point P. is going to be same at all points, right? This will be the same at all points. So any point on the surface is the same. So this is going to be this same answer as that, but I got it through these two arguments applied to Gauss's law. And this is a very important set of arguments, okay? And we're going to do it one couple more problems using this argument of a spherical symmetry now. And then in the next couple of videos, I'm going to do cylindrical symmetry and planar situations, okay? So the number, let's do the number 3. I'm going to clean up and try to do number 3. Okay. You haven't, just an announcement, if you haven't subscribed to this channel, please subscribe to this channel. It helps grow this channel and make it accessible to more and more people. It's more easily discoverable on YouTube. Also, you may want to check out my website, which is physicsbootcamp.org. Okay. Back to here. Now we have a situation where you have a spherical charge distribution. So you have a spherical surface, maybe a ball, a metal ball, and you put some charge on it, and it's kind of distributed evenly. So this is actual ball, and surface charge is only on the surface. So there's a Q amount of charge distributes evenly on the surface, and we want to know what's the electric field at a point P outside, okay? And then there's a P which is inside, not on the surface. P inside, not on the surface. At this point, we'll do this one and then we'll do this one. So I want to know what's the electric field here. Okay, so when you look at these charges, right? So there is some charge here, 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 right? So let's look at any charge. Each charge is going to produce its electric field that way. This one is going to produce electric field that way. This is going to produce electric field that way. This is going to produce electric field that way. Well, it will be very complicated, right, to figure out from each one of these. You can integrate it. See each one of the charges, and then you can add up and integrate it. However, we can say from this symmetry that if this is the center, from, if you look at the ring, you can think of this as rings, from any direction. So the ring, from each one of the rings, you're going to have electric field is going to be in this direction from each one of the rings, and then all the rings will kind of add up, right? So it's going to be straight out like that. Now we need to imagine, so imagine a spherical surface which is at distance, from the center of this, from O to point P, less distance R. So this is the surface. Imagine surface S, and at each one of these points of the surface, if you look at the electric field will be, by the same argument, from the symmetry of the charge, you can use these rings, right? And you can show that this is that way. So electric field at this point, which is distance R. And so this is point, say, P2, okay? Point P2 and point P out, the magnitude of the electric field has to be the same, right? Because it's the same symmetry situation. So on this surface we notice electric field has same magnitude at all points. This, and second thing we notice on this surface is the direction of the electric field. If these are positive charges, the direction is this way. If the negative charge, the direction is that way. And on this surface, if you look at the normal, which where the normals are, normal are pointed radially out, right? On a spherical surface, the normal is just like a point charge situation, n hat. So electric field vector for each patch is parallel to n hat at that patch, and so that E vector dot n hat is equal to just E. So either is going to plus or minus E, and we have because of the other term this way for positive charges, and for the negative charge electric field will be that way. For if the charges were negative, this guy is negative. So this, but we can absorb this into this and just call this E. Okay. And the situation is similar. So we do E dot NdA on this surface, and that's equal to same E, E times dA, same E at every point of this surface, so this comes out, and E times 4 pi r square. So the left side of Gauss is like this, and the right side, how much charge did get enclosed? All of it. I enclosed all of it. So this is the whole of this. Q enclosed is Q. And so once again we get E at P out is Q over 4 pi r square, 4 pi epsilon naught r square, epsilon naught r square. So this is the magnitude, and of course the direction is, if I'm looking at here, from the center to that point outward, from center to that point onward, wherever we're looking. So to write the direction, we're gonna write down formula E at P out any point on will be equal to Q over 4 pi epsilon naught r square, and U hat will be from O, the center of the sphere, to the P out. So that's the full answer. Okay, so what will be at a point inside? So I do exactly the same argument. I really don't need to erase anything. It's very trivial. If I look at, let's look at, so this is inside. So imagine, so this is the P in here, and this is the S2. And if I do an S2, from the same kind of symmetry argument, so this is, let's call it E in, and let's call this R in. So same argument, go through that, and we get this. But on the right side, what's the charge enclosed inside here? Actually, no charge is enclosed. This is actually 0. So the right side is 0. So E in, this equal to 0. This is not 0. This just means E in equal to 0. So if you have a spherical cell, all the charges are on the spherical surface. If I take a surface inside which is smaller than where the charges are located, electric field will be 0. So in a spherical shell, this is really very important discovery in a way. It's very easy to get it using Gauss's law. That if I have a spherical shell, charges are here, so charges are here, then the electric field here is 0. So this is R in. So inside, if you are inside, you won't feel any electric field. And this is the reason for Faraday cage. You probably studied that. Maybe you should look it up. Faraday cage. Okay, there's one more problem that we should do for a spherical symmetry. Okay, now this is a solid sphere and not spherical shell, a solid sphere. We want to know P electric field at a point outside and electric point inside. So it's going to go exactly same way, right? For the outside, if I do outside, so this is the surface, and when we work out, I'm going to get at a point out at this point, and times 4 pi, let's see, r out square from the center is equal to, I'm have entire charge enclosed, so 4/3 pi, you have r cube times rho. This is the entire charge enclosed, and divided by epsilon naught. So this is outside, and you can just see that the electric field goes as let's 4/3 pi r cube rho over 4 pi epsilon naught 1 over r square. R is greater than r. I can write r out as this way. So this is at any point P that's outside. I'm going to have that formula. That's just very simple. It looks like a point charge, as if the entire charge was placed right over here. So this is the same formula as if the entire surface. So this is the Q total. Q total was placed at one point, and the point P was a distance r out, and the sphere is, it doesn't matter what the sphere size is, right? As long as r is outside, this point P is outside. Okay. How about for inside? The inside is the interesting part. If I look at the inside, now it's not going to be 0 because the charge enclosed is it depends on the size of the sphere, how much charge are enclosed. So for the inside, E inside 4 pi r inside square is equal to 4/3 pi, not total r, but r inside cube rho over epsilon naught. So if I write r in as just r less than r, right? Rather than use in, etc., just use the regular symbol for radial distance. So at a point E inside is 4/3 pi r cube rho over 4 pi r square epsilon naught. So you can see a whole bunch of cancellation here. 4 pi go away, r square go away. So we have a epsilon naught 3 epsilon naught rho times r, and this one is if I write this down, it's going to be cancel 4 pi, so I have a 1 over 3 epsilon naught, I have a r cube rho 1 over r square. So you can see that electric field, if I were to draw this magnitude, this guy's is okay with distance r, and here is at the size of the sphere. So this is linearly goes up with r, so it goes up with r, and then outside it actually drops as 1 over r square. So this is pretty interesting. If there's a you can see there's a right at r, there is a there's a jump in the derivative, right? It just go this way and then it's going that way. Okay, you can see I got this formula quite easily, but if you try to do the integral not using Gauss's law, these integrals are very hard to do without doing Gauss's law. Okay, by integral I mean electric field using the basic definition, electric field at some point P using 1 over 4 pi epsilon naught dq over r square. You had using this formula would be very hard to do other than this. Okay, I'm going to stop here. Next up for Gauss's law are the problem in kind of cylindrical symmetry, like infinitely long wire or infinitely long cylinder, and they're filled with charges, what the electric field will be. Okay, see you later. Bye.